Imagine you accidentally touch a red-hot stove burner.
Oh, yeah. The world.
Right. Within milliseconds, a signal travels from the nerve endings in your fingertip, shoots up your arm, hits your spinal cord, and just rockets straight up to your brain.
And your brain registers that massive threat immediately. It screams danger.
Exactly. And it instantly fires a signal back down to your muscles, violently jerking your hand away. I mean, that instantaneous reaction is the nervous system functioning perfectly.
It really is. It's the body's ultimate life-saving alarm system.
But consider a totally different scenario. You pull your hand away, the burn heals up, the fire is completely extinguished, but that alarm, it refuses to shut off.
Wow. So the brain just keeps getting that signal.
Yeah. Your brain continues to perceive the sensation of burning tissue 24 hours a day, 7 days a week, for years.
Which transforms the nervous system from a protective mechanism into, well, a prison. The alarm itself actually becomes the threat.
And that is the exact phenomenon we are investigating today on this deep dive. We're looking at this through the lens of a really fascinating 2017 medical paper.
Right, the Oredo paper.
Yep. It's titled Relating Chronic Pelvic Pain and Endometriosis to Signs of Sensitization and Myofascial Pain and Dysfunction.
Quite a mouthful.
It really is. But it was authored by Jacqueline Oredo and a team of researchers from the National Institutes of Health and the University of Rochester. And, we're going to unpack why traditional medical treatments for chronic pain so often fail.
Because doctors are basically treating the visible anatomy of a disease while completely ignoring the invisible neurobiology and the musculoskeletal fallout.
Exactly. So whether you're studying for an AP bio exam, thinking about a career in medicine, or just insanely curious about how your own body's wiring can go rogue, you are in the right place.
The paradigm shift here is just profound. For a very long time, medical science treated chronic pain as merely a symptom of an underlying anatomical injury.
Like if you fix the injury, the symptom should just disappear.
Right. But this paper forces us to look at cellular inflammation, the literal structural rewiring of the spinal cord, and the cascading effects that turn healthy muscles into rigid traps.
We'll even explore how medical science uses some of the most potent biological toxins on Earth to hack that corrupted nervous system.
It's wild stuff. But to ground this discussion, we really need to establish the clinical reality of the patients at the center of this paper.
Okay, let's start there.
The condition is chronic pelvic pain, or CPP. In the medical literature, this is defined as persistent, non-cyclic pain located below the umbilicus, the belly button that has lasted for a minimum of 6 months.
Half a year of continuous debilitating pain. I mean, the psychological and physical toll of that is just staggering to even think about.
It completely alters every single aspect of a person's life. And when clinicians investigate the root cause of CPP, the statistics point heavily in one specific direction.
Endometriosis, right?
Yes. Between 71 and 87% of women presenting with chronic pelvic pain have laparoscopically proven endometriosis.
Laparoscopically proven, meaning a surgeon has actually gone in and seen it.
Exactly. A surgeon made an incision, inserted a camera, and visually verified the presence of ectopic endometrial lesions.
Okay, let's break that biology down for a second for our listeners. Endometrial tissue normally lines the inside of the uterus, right? It thickens and sheds during the menstrual cycle.
Right, that's normal physiology.
But in endometriosis, tissue that is biologically similar to that lining starts growing outside the uterus.
Yeah, it implants on the ovaries, the fallopian tubes, the outer surface of the uterus, or even just the tissue lining the pelvic cavity.
Which leads us to the prevailing medical hypothesis that has totally dominated gynecology for decades, basically. The lesions themselves are the sole generator of the pain.
It seems logical, doesn't it? The logic follows that if you surgically remove or chemically suppress these abnormal growths, the patient will be cured.
It makes complete intuitive sense. I like to think of it as the rock in the shoe model of medicine.
Oh, I like that. How does that work?
Well, if you have a sharp rock in your shoe, your foot hurts exactly where the rock is pressing into your heel, right?
Right.
You take the shoe off, dump the rock out, and the pain immediately resolves. The cause and effect are perfectly linked.
Yeah.
But the clinical data for endometriosis drastically contradicts this model.
It really does. The standard therapies, hormonal suppression to starve the tissue or surgery to cut it out, frequently fail to stop the pain.
And the failure rate of surgical intervention for long-term pain resolution is just one of the most frustrating aspects of this disease for patients and doctors.
Definitely. And the Oredo paper highlights a really critical, observable discrepancy that breaks your rock in the shoe analogy completely.
What's that?
The location of the visible lesions correlates very poorly with where the patients actually experience the pain.
Okay, that is the piece of data that should make any grade 12 science student pause and rethink their entire premise.
Absolutely. You could have a surgeon find a tiny solitary lesion on a patient's left ovary, just
Yeah.
one tiny spot. Yet that patient reports severe, radiating, agonizing pain across her entire right lower back and pelvic floor.
Wow. So a purely anatomical, localized view of disease just cannot account for that.
No, it can't. If the pain persists after the ectopic tissue is removed, or if the pain shows up in areas completely devoid of lesions, it means the pain is no longer tethered to the tissue.
The disease has migrated from the tissue into the communication network itself. I mean, hardware might be clean, but the software is completely corrupted.
That's a great way to put it. To understand the mechanism of that corruption, we have to zoom way in. We need to examine what these lesions are actually doing on a microscopic level.
Because these aren't just inert scabs, right?
Not at all. Endometriosis lesions are highly active, living tissues growing in a hostile environment outside the uterus.
And to survive, they need a robust supply chain of oxygen and nutrients. Basically, they need a blood supply.
Which triggers a biological process called angiogenesis.
Okay, angiogenesis, let's define that.
It's the physiological process through which new blood vessels form from pre-existing vessels.
So the lesions are basically calling out for blood.
Exactly. The ectopic lesions secrete chemical growth factors into their surrounding environment. These factors bind to receptors on nearby blood vessels, tricking the vascular system into sprouting new capillary branches.
Wow, so the blood vessels literally grow toward the lesion to feed it.
Yes, but the body's systems don't operate in isolated silos. When we look at the cellular biology described in this paper, the overlap in molecular signaling is just incredible.
Right, because the same chemical factors that stimulate the branching of blood vessels also have a profound effect on nerve fibers.
Which introduces a major player here, nerve growth factor, or NGF.
NGF. And researchers analyzing the tissue of these endometriosis lesions find highly elevated concentrations of it.
They do, and nerve growth factor does exactly what its name implies. It promotes the survival and growth of neurons. Specifically, it drives something called neurite outgrowth.
Neurite outgrowth. Think of that like a nerve cell sprouting new branches, extending its reach like a tree growing roots toward a water source.
Perfect analogy. Because the lesion is pumping out NGF, it actively attracts sensory neurons and nociceptors.
Nociceptors being your body's specialized pain receptors.
Right. This is a devastating biological accident. The lesion is just trying to get a blood supply to survive. It secretes growth factors to attract capillaries.
But in doing so, it inadvertently lays down high-speed nerve pathways directly into its own tissue.
Yes, it gets infiltrated by both sensory fibers, which carry pain signals back to the brain, and sympathetic nerve fibers, which regulate autonomic bodily functions.
It's like the body is accidentally laying down high-speed fiber optic cables directly from this rogue tissue straight to the brain's alarm center. The lesions are hacking the body's own infrastructure.
They absolutely are. They physically bridge themselves right into the central nervous system. But, the mere presence of these new nerves isn't what causes the agony.
It's not.
No, the environment surrounding these nerves is what triggers the cascade. The peritoneal fluid, the liquid that bathes the organs within the pelvic cavity in a patient with endometriosis, is highly toxic to these new nerve endings.
The paper refers to it as an inflammatory soup.
A very nasty soup.
Yeah. If we look at the specific ingredients of this soup, it reads like a rogues gallery of the immune response. For anyone studying immune biology, this is key.
We're talking about massive concentrations of tumor necrosis factor alpha, interleukins like IL-1, IL-6, and IL-8, and various prostaglandins.
So cytokines and lipid compounds. Now, in a normal, healthy immune response, say you get a paper cut, these molecules rush to the site, right?
Exactly. They cause local blood vessels to dilate, which creates heat and redness.
They make the blood vessels leaky so white blood cells can slip into the tissue to fight bacteria, causing swelling.
And they sensitize local pain receptors, so to protect the injured area. That acute response is designed to last for a few days until the tissue heals.
But with endometriosis, the immune system is constantly attacking the ectopic tissue, and the tissue is constantly fighting back.
So that acute inflammatory response becomes a chronic, localized war zone. And those newly sprouted pain receptors are bathing in that inflammatory soup 24 hours a day.
Man, and these specific cytokines have a potent direct effect on those nociceptors, lowering their activation threshold.
Let's delve into the mechanics of that because this touches on the fundamental physics of how our nervous system operates.
Oh, this is the good stuff. Grade 12 bio students. Listen up. Neurons run on electricity.
They do. They maintain a specific voltage across their cell membrane, known as the resting potential.
Right. The inside of the cell is negatively charged relative to the outside, and this is maintained by specialized proteins pumping sodium and potassium ions back and forth.
Right. So for a nerve to fire a signal, an action, potential, a stimulus, must be strong enough to open those ion channels and flood the cell with positive ions.
Pushing the voltage past a specific threshold. And once that threshold is breached, the neuron fires an all-or-nothing electrical pulse down its axon.
In a healthy nerve, that threshold is set relatively high to prevent false alarms. You have to touch a pan that is actually burning hot to trigger it.
But constant exposure to molecules like prostaglandins and tumor necrosis factor completely alters the chemistry of the nociceptor's membrane.
The nerve adapts to its toxic environment. It actually changes its gene expression to manufacture and insert more sodium channels into its membrane.
Wait, really? It physically builds more channels.
Yes. And with more channels available, the resting potential shifts dangerously close to the firing threshold.
So the threshold drops. A stimulus that normally wouldn't generate enough voltage to trigger an action potential suddenly causes the nerve to fire.
This is the scientific definition of peripheral sensitization.
It's akin to taking a car alarm that used to only trigger if someone smashed a window and rewiring it so it goes off if a leaf falls on the hood.
That is a perfect way to visualize it. Peripheral sensitization makes the nerves incredibly hyperexcitable. But the pathology goes even deeper than just sending amplified signals to the brain.
How much deeper can it go?
Well, these nociceptors also start firing backwards into the tissue.
Oh, the antidromic release, right. The nerve endings themselves become active participants in the inflammation.
Exactly. The sensitized nerve terminals secrete neuropeptides directly into the surrounding peritoneal fluid.
And the two major culprits here are substance P and calcitonin gene-related peptide, CGRP.
Right. And those neuropeptides are incredibly powerful vasodilators. They force the local blood vessels to widen even further and become even more permeable.
Which recruits even more immune cells to the area, creating a state called neurogenic inflammation.
It's wild. The inflamed tissue sensitized the nerve, and now the nerve is dumping chemicals that further inflame the tissue.
It is a perfect catastrophic feedback loop.
It really is.
But everything we've described so far is still happening out in the periphery, in the pelvic cavity. So how does this localized war zone end up rewiring the spinal cord and the brain itself?
It essentially comes down to volume and duration. This unending activation of the nociceptors generates a massive afferent bombardment.
Afferent, meaning neural signals traveling from the periphery toward the central nervous system.
Yes. This relentless, high-frequency barrage of pain signals travels up the sensory nerves and slams into the dorsal horn of the spinal cord.
The dorsal horn. That acts as the spinal cord's main receiving dock and processing center for sensory information.
Right. It's supposed to filter and relay signals up to the brain.
Yeah.
But it isn't designed to handle a permanent maximum volume alarm.
I can imagine. So what happens?
Just as the peripheral nerves adapted by adding ion channels to lower their threshold, the interneurons within the dorsal horn adapt to the constant bombardment.
Wow.
The sustained influx of pain signals physically and functionally restructures the central circuitry. The synapses between the incoming nerves and the spinal neurons become stronger and more sensitive.
The spinal neurons themselves change their resting potentials. And this is central sensitization.
Yes. The spinal cord essentially undergoes pathological learning.
Pathological learning. So the spinal cord actually learns to be in pain.
It does. It becomes incredibly efficient at processing pain signals to the point where it starts amplifying them.
The clinical manifestations of a central nervous system locked in this state must be profound.
They are. Patients develop hyperalgesia and allodynia.
Okay, let's define those. Hyperalgesia being an exaggerated response to a painful stimulus. So like an exam that might normally feel mildly uncomfortable to a healthy patient feels excruciating and sharp.
Exactly. And allodynia is even more distressing. It is the perception of pain from a stimulus that is completely non-noxious, something that should not hurt at all.
Such as the light brush of clothing against the abdomen. Or even internal, normal physiological functions like the movement of digestion or the bladder filling with urine.
Because the spinal circuitry is so hyperreactive, it takes normal, innocuous sensory input from the pelvic organs and the skin, amplifies it, and misinterprets it as a severe threat.
I look at that mechanism and think about the implications for surgery.
Oh, they're huge.
Because if the spinal cord has structurally reorganized itself to amplify pain, and the dorsal horn neurons are now firing spontaneously, even with minimal input, does it even matter if the surgeon removes the original endometriosis lesion?
That is the tragic reality for so many patients, and it's the core thesis of this paper. Once central sensitization becomes entrenched, the dynamic alterations within the central nervous system can perpetuate the perception of pain long after the initiating pathology is gone.
The pain has decoupled from the lesion. The pain is no longer a symptom. It has become its own independent disease state.
Exactly, and that fundamentally changes the diagnostic approach.
Because if you are a doctor looking purely at the tissue, you will tell a patient whose lesions have been removed that they are cured, and that their ongoing pain has no physical basis.
Which is a horrific thing to tell a patient who is trapped in central sensitization. It leads to immense medical gaslighting.
Oh, absolutely. But central sensitization, while explaining the intensity and persistence of the pain, it doesn't fully explain the geographic spread of the pain.
No, it doesn't.
Why do patients with endometriosis develop agonizing pain in completely healthy skeletal muscles?
Yeah.
In their lower back, their abdomen, and their pelvic floor?
That's the part that really made me reconsider how evolution designed our bodies.
Yeah, because if the rogue nerves are sprouting into the reproductive organs, why are the muscles of the pelvic floor getting dragged into the collateral damage? They seem like two completely separate systems.
To understand that collateral damage, we have to look at the architectural quirks of our neuroanatomy, specifically a phenomenon known as viscerosomatic convergence.
Viscerosomatic convergence. Let's break those terms down. Visceral relates to the internal organs, the uterus, ovaries, bowel, bladder.
Right.
Somatic refers to the body, the skin, skeletal muscles, joints. And convergence means coming together at a single point.
Exactly. And here's the thing. We possess a surprisingly low number of visceral sensory nerves.
How low are we talking?
The afferent fibers transmitting sensory data from all of your internal organs make up roughly 2 to 7% of the total afferent fibers entering the spinal cord.
Only 2 to 7%. I genuinely struggle to understand why evolutionary biology would leave us with such a minimal internal security system.
It seems counterintuitive, right?
Totally. You would think our vital internal organs would have the most robust, highly localized pain mapping possible. Like, if my appendix is inflamed, I want to know exactly where that is.
From an evolutionary perspective, it makes sense when you consider the ancestral environment. We evolved primarily to detect and evade external threats.
Right, like a predator biting a limb, a sharp rock cutting our foot, extreme heat or cold.
Exactly. The somatic nervous system needs immense precision so we can react instantly to an external danger. Conversely, internal organ damage or rupture was almost universally fatal in a pre-medical world.
Oh, wow. So there was no evolutionary advantage to developing highly precise, localized visceral pain mapping because there was nothing early humans could do to fix an internal organ injury anyway.
That is the brutal but logical reality of natural selection.
So because these visceral nerves are so sparse, they don't get their own dedicated private pathways up the spinal cord to the brain.
They don't. Instead, the visceral nerves enter the dorsal horn and converge onto the exact same second-order interneurons that receive somatic input from the muscles and skin of the same general region.
I think of this like a networking issue in a massive office building.
Oh, let's hear it.
You have a central router, which is the interneuron in the spinal cord. Plugged into port A on that router is a computer representing the internal organ, say the uterus.
Okay.
Plugged into port B on the exact same router is a computer representing a skeletal muscle in the lower back.
And the server receiving the data of the brain is notoriously terrible at deciphering which specific port sent the signal when the traffic comes from a shared router.
Right. So when a massive wave of pain signals from the inflamed endometriosis tissue hits that shared interneuron, the interneuron fires up to the brain.
And the brain receives the alarm, but it has to guess the origin. And because somatic injuries are statistically vastly more common than visceral ones, the brain defaults to the somatic pathway.
The brain literally misinterprets the organ pain as muscle or skin pain.
Yes. It projects the sensation onto the somatic structures innervated by that shared spinal segment. This is the physiological mechanism behind referred pain.
It's like the classic heart attack symptom.
Exactly. The heart muscle becomes ischemic, but the patient feels a crushing pain radiating down their left arm or up into their jaw.
Because the heart and the left arm share a spinal router, and the brain assumes the arm is under attack.
Precisely. In chronic pelvic pain, the relentless visceral input from the endometriosis is perceived by the brain as agonizing pain in the lower back, the abdominal wall, and the pelvic floor.
That makes so much sense. But this convergence isn't merely a sensory illusion, is it? It has a physical component, too.
It has a catastrophic motor component.
The viscerosomatic reflex. The sensory pain signal doesn't just go up to the brain, it actively triggers a physical movement response locally in the spinal cord.
Yes. The visceral nociceptors synapse onto sensory interneurons, but they also branch off and synapse onto interneurons that activate motor neurons in the anterior horn of the spinal cord.
Specifically, the alpha and gamma motor neurons that dictate the contraction of skeletal muscle.
Right. So, the massive pain signal coming from the inflamed organ accidentally triggers a contract command that shoots out to the surrounding skeletal muscles.
Wow. So the presence of ongoing visceral inflammation triggers what clinicians call guarding reflexes.
Yes. The central nervous system detects severe trauma in the pelvis. It relies on a primitive protective mechanism. It fires motor signals to tighten and lock down the skeletal muscles surrounding the area.
It is attempting to splint the region, basically putting a muscular cast around the internal organs to prevent movement and further injury.
It's a protective reflex that has completely misread the situation. Flexing your pelvic floor muscles as hard as possible isn't going to heal an ectopic lesion on your ovary.
It definitely won't. And because the visceral pain signal never stops, the motor command to contract the muscles never stops.
Which leads to the next major physical pathology of chronic pelvic pain, the formation of myofascial trigger points.
Okay, if you've ever had a deep tissue massage, you've probably had a massage therapist tell you they found a knot or a trigger point in your upper back or shoulder.
We've all been there.
But what we are talking about in the context of chronic pelvic pain is a fundamentally more severe and entrenched pathology.
It is. A myofascial trigger point, abbreviated as an MTRP, is clinically defined as a hyperirritable spot located on a taut band of skeletal muscle.
And the critical factor here is that this specific band of muscle fiber is locked in a sustained, continuous state of contraction.
In the pelvic region, we are looking at muscles that form a sling at the bottom of the pelvis. Muscles like the levator ani complex, the coccyges, the obturator internus.
These muscles support the bladder, the bowel, and the uterus. And when they develop trigger points, they don't usually feel like small, round marbles, right?
No, they present as incredibly tight, rigid, ropey bands that span the length of the muscle.
To understand why a trigger point is so painful and why it refuses to relax, we have to zoom down into the microscopic machinery of muscle contraction.
Time for the sliding filament theory.
Yes. Inside every muscle fiber are repeating units called sarcomeres. And inside the sarcomeres are two primary protein filaments: actin, which is thin, and myosin, which is thick and has these little golf club-shaped heads.
Right. When a motor nerve sends a signal for a muscle to contract, it releases acetylcholine at the neuromuscular junction.
This triggers a cascade that releases calcium ions inside the muscle fiber, and the calcium exposes binding sites on the actin filament.
And the myosin heads immediately grab onto those exposed sites, forming a cross bridge. They flex, pulling the actin filaments toward the center, which shortens the muscle.
That's the contraction. But here is the crucial part that often gets overlooked. Releasing that grip requires energy.
It requires ATP, the primary energy currency of the cell. An ATC molecule must bind to the myosin head to force it to let go of the actin so the muscle can relax.
But in a myofascial trigger point, that panicked spinal cord is constantly firing motor signals, screaming at the muscle to contract. The myosin heads are locked onto the actin, pulling tight.
And the sustained contracture physically bulges the muscle fiber, which violently compresses the microscopic capillary blood vessels running through the muscle tissue.
So the muscle essentially strangles its own blood supply.
Yes, creating a localized zone of profound ischemia, a severe lack of oxygen and fresh blood flow.
And without blood flow, no fresh oxygen or glucose can get in to manufacture ATP.
And without ATP, the myosin heads cannot detach from the actin. The contraction becomes physically locked.
Furthermore, without oxygen, the struggling muscle tissue is forced to switch to anaerobic metabolism to try and survive.
And we know from bioclass, a byproduct of anaerobic metabolism is lactic acid.
Right. Because the blood vessels are compressed, this acid cannot be flushed away. It pools in the tissue.
So you have a muscle fiber that is locked rigid, suffocating from lack of oxygen, and marinating in its own acidic waste.
That sounds awful. And that localized acidic environment is incredibly noxious. It directly stimulates the sensory nerve endings located within the muscle itself.
Which fires a massive new wave of somatic pain signals back up to the already traumatized, sensitized spinal cord.
And there is the final horrifying piece of the puzzle.
The initial inflammation from the endometriosis caused the spinal cord to panic.
The panicked spinal cord reflexively caused the pelvic muscles to cramp to protect the organs.
But now that locked muscle cramp is generating its own intense ischemic pain signals, which are firing right back into the central nervous system.
It creates a self-sustaining vicious feedback loop independent of the original disease.
Exactly. The pain from the muscle exacerbates the central sensitization, and the central sensitization keeps the motor neurons firing, locking the muscle further.
Even if a surgeon perfectly excises every microscopic trace of endometriosis at this stage, the loop between the spinal cord and the pelvic floor is already self-perpetuating.
The trigger points themselves become primary pain generators. They can be active, meaning they spontaneously generate pain constantly, or they can be latent, meaning they are painfully tender only when touched or stretched.
And the paper details how these trigger points refer pain in incredibly deceptive ways.
They really do. Trigger points in the levator ani or obturator internus frequently refer intense, stabbing pain to the urethra, the vagina, the rectum, or the lower back.
Think about the clinical nightmare that creates. A patient goes to an urgent care clinic or a specialist complaining of severe burning pain when urinating, agonizing pain during bowel movements, and crushing lower back pain.
And the standard medical response is to evaluate the organs located where the pain is felt. The doctor will order a urinalysis and cultures for a urinary tract infection.
They might schedule a colonoscopy to check for inflammatory bowel disease.
They might order a lumbar MRI to look for a herniated disc pressing on a nerve.
And all of those tests will come back completely negative. Because the bladder is perfectly healthy, the bowel is healthy, the spine is fine.
The actual source of the pain is a microscopic traffic jam of actin and myosin locked in a rigid band in the pelvic floor, driven by a corrupted software loop in the spinal cord.
This illustrates precisely why the authors of this paper argue that the standard gynecological or gastrointestinal evaluation is just grossly inadequate for chronic pelvic pain patients.
You cannot diagnose a complex neuromusculoskeletal software corruption with a purely anatomical hardware exam.
Right. So if the speculum and the standard ultrasound are missing the root cause, what does a proper diagnostic evaluation actually look like?
The paper outlines a comprehensive dual-pronged approach. The evaluation must shift to diagnosing the musculoskeletal and neurological dysfunction.
Okay, so what's the first component?
It's a targeted, highly specialized pelvic floor examination.
How does it differ mechanically from what a patient usually experiences at the gynecologist?
Well, a standard bimanual exam is generally looking for masses, cysts, or the anatomical position of the uterus and ovaries. It is not designed to assess muscle tone.
The paper recommends a single-digit examination instead, right?
Literally just using one finger, yes. The clinician uses a single digit to move incredibly slowly and methodically, mapping the musculature.
They start externally and move internally, deliberately palpating specific individual muscles of the pelvic floor sling.
They aren't looking for tumors. They are feeling the texture of the tissue, searching for those taut, rigid, ropey bands of muscle fiber that indicate a trigger point.
And crucially, when they find a tight band, they apply sustained pressure to see if it reproduces the patient's familiar pain symptoms.
If pressing on the obturator internus muscle instantly triggers the severe urethral pain the patient has been complaining about, the clinician has positively identified the source of the referred pain.
It reminds me of trying to find an electrical short in a house. You don't just stare at the light bulb that keeps flickering.
No, you have to trace the wire back, open the wall, and systematically test the breaker box to find where the signal is actually degrading.
That's a great way to put it. And a good electrician doesn't just check the one breaker, they check the whole board.
Which brings us to the second component of the evaluation, a broad, systemic neuromusculoskeletal exam.
And the goal here is to map the physical extent of the central sensitization. We talked earlier about allodynia feeling pain from a light, non-noxious touch. How does a doctor formally test for that across the body?
They map the dermatomes.
A dermatome being an area of skin that is primarily supplied by a single spinal nerve.
Exactly. The clinician will use a technique called pinch and roll. They gently pinch a small fold of skin and subcutaneous tissue, usually over the abdomen or lower back alongside the spine, and roll it between their thumb and fingers.
Now, in a healthy person, that just feels like a minor stretch of the skin.
But in a patient whose spinal cord has become heavily sensitized, rolling that skin will feel incredibly sharp, burning, or intensely painful.
Wow. It maps exactly which spinal segments are hyperreactive.
Mm.
The paper also mentions testing for hyperalgesia, the exaggerated pain response, using tools that sound distinctly medieval.
You're talking about the Wartenberg pinwheel.
Yeah, it's a small medical instrument consisting of a handle and a little rotating wheel with sharp radiating spokes, resembling a tiny spur.
Right. The clinician rolls the spiked wheel gently across the skin, applying just enough pressure to elicit a tactile, slightly sharp sensation.
Normally, it just feels like a mild scratch.
But if they roll it over a sensitized dermatome, the central nervous system amplifies the input, and the patient experiences severe, disproportionate pain.
And the truly mind-bending part of this evaluation is how far they look beyond the pelvis. They map myotomes, groups of muscles innervated by a single spinal nerve root, working their way up the entire body.
They check for trigger points in the rectus abdominis, the hip flexors, the lower back, and they keep going up.
They evaluate the trapezius muscles in the shoulders. They even evaluate the masseter muscle in the jaw.
Yes, the jaw.
I have to pause on that. Why on earth would a doctor diagnosing chronic pelvic pain check the jaw muscles?
Because the central nervous system is a single, continuous entity. If the central sensitization driven by the pelvic pain has become severe enough, it can cause changes that migrate up the spinal cord, altering excitability at higher levels.
And additionally, chronic, unremitting severe pain causes a systemic, whole-body stress response.
Right. The patient might be unconsciously clenching their jaw day and night as a physiological reaction to the agonizing pain in their pelvis.
Finding active myofascial trigger points in the masseter muscle tells the clinician a crucial story about just how deeply and extensively the patient's entire nervous system has been compromised by the disease process.
It proves that a localized pelvic approach will never be enough.
So a specialist conducts this exhaustive evaluation. They map the sensitized dermatomes with the pinwheel, they isolate the top bands and the levator ani, they find the trigger points.
They have mapped the corrupted software and the locked hardware.
But the ultimate question is, how do we break the loop? If the muscle is physically locked and the nerve is chemically hypersensitive, how do we force a system reset?
Treatment requires a multidisciplinary assault on the pathology. The foundational layer is specialized pelvic floor physical therapy.
But it is vital to emphasize that this is not about doing Kegel exercises to strengthen the muscles. Strengthening a muscle that is already locked in a severe spasm will only cause more ischemic pain.
Definitely. The goal isn't strength, the goal is release.
The physical therapist utilizes myofascial release techniques. This involves applying highly specific, sustained, deep pressure directly onto the trigger points, combined with targeted stretching and joint mobilization.
They are physically trying to stretch out those locked sarcomeres, separate the actin and myosin, and force blood back into the ischemic tissue to flush out the lactic acid.
But for many patients who have been trapped in this loop for years, physical therapy alone isn't enough. The sarcomeres are too rigidly locked. The central sensitization is too deeply entrenched.
The manual pressure from a therapist's finger just can't penetrate the taut band. That is when medical intervention brings out the needles.
Trigger point injections, or MTRP injections, become a critical tool for breaking refractory cases. The paper details two primary methodologies: dry needling and wet needling.
Dry needling is a term that inherently sounds painful.
Yeah, it does. What is the mechanism of action there?
The clinician inserts a very fine, solid filament needle directly through the skin and into the hypercontracted taut band of the muscle. There is no medication in the syringe.
So the mechanism of action is entirely mechanical disruption. You're essentially taking a tiny spear and stabbing the microscopic knot of locked proteins.
Yes, when the needle pierces the trigger point, the mechanical trauma physically disrupts the dysfunctional motor end plates. It routinely elicits what is called a local twitch response.
A sudden involuntary spinal cord reflex, where the muscle fiber violently twitches.
Exactly. And that violent twitch acts like a circuit breaker tripping. The sudden, chaotic contraction forces the locked actin and myosin to spontaneously decouple.
It mechanically forces the muscle to let go, instantly relieving the physical tension and breaking the aberrant sensory signal. It resets the tone of the muscle.
Now, wet needling takes that same mechanical disruption, the needle piercing the knot, and combines it with a chemical intervention.
The clinician injects a local anesthetic, typically lidocaine or bupivacaine, directly into the core of the trigger point.
The lidocaine acts as a chemical block. It shuts down the sodium channels on the sensory nerves located within the muscle, completely preventing them from firing action potentials.
Ah, so you get the mechanical release of the muscle fiber from the needle, and the lidocaine silences the screaming sensory nerves, finally stopping the barrage of pain signals hitting the dorsal horn.
It provides the central nervous system a desperately needed window of silence to begin winding down the sensitization.
But lidocaine is temporary, right? It metabolizes and wears off in a matter of hours or days.
It does. And if the spinal cord is still hyperreactive, it might just start firing motor signals again once the anesthetic is gone, relocking the muscle.
So for the most severe, intractable cases, the paper outlines a treatment protocol utilizing a profoundly powerful, long-lasting neurotoxin.
Yes, this is the application of botulinum toxin type A, commonly known as Botox.
Most people hear Botox and immediately think of cosmetic dermatology smoothing forehead wrinkles.
Right. But its application in neurology and pain management is arguably its most vital medical use.
To understand how it works, we have to look closely at its origin and its terrifying biological potency. Botulinum toxin is produced by the bacterium Clostridium botulinum,
It is the causative agent of botulism.
and it is universally recognized as one of the most acutely lethal biological substances known to humanity.
Ingesting even microscopic amounts of the raw toxin causes systemic irreversible paralysis of skeletal muscles, ultimately leading to death when the respiratory muscles fail.
The medical use of Botox relies on extreme purification, microscopic dosing, and incredibly precise, localized injection.
We need to go back to the neuromuscular junction to see how it works. That tiny gap between the motor nerve terminal and the muscle fiber.
We established earlier that the nerve releases the neurotransmitter acetylcholine into this gap to command the muscle to contract. Let's look at the exact mechanics of that release because that is what Botox destroys.
Okay, inside the nerve terminal, the acetylcholine is stored in tiny bubbles called synaptic vesicles.
When an action potential arrives, these vesicles must travel to the cell membrane and dump their contents into the gap.
To do this, they rely on a complex of specialized proteins known as snare proteins.
Think of snare proteins as a highly sophisticated docking mechanism. They act like molecular winches that grab the vesicle, pull it tight against the cell membrane, and fuse them together so the acetylcholine can spill out.
Botulinum toxin is a highly specific protease enzyme. When injected into the muscle, it is taken up by the motor nerve terminals.
Once inside, the Botox enzyme acts like microscopic scissors. It targets and physically cleaves snips in half the snare proteins.
The docking mechanism is completely obliterated.
The motor nerve is still perfectly alive. It still generates an action potential. It still manufactures acetylcholine and packages it into vesicles.
But without the snare proteins to dock and fuse the vesicles to the membrane, the neurotransmitter is trapped inside the cell. It cannot be released into the synapse.
The chemical bridge between the nervous system and the muscular system is completely severed.
The brain and spinal cord can scream at the muscle to contract as loudly as they want, but the muscle never receives the message. It is chemically forced to remain paralyzed and completely relaxed.
And because the Botox physically destroyed the snare proteins, this blockade is highly durable.
The nerve terminal cannot function again until the neuron slowly synthesizes brand new snare proteins and physically sprouts a new nerve ending, a process that typically takes 3 to 6 months.
For half a year, that specific muscle fiber cannot spasm. The ischemia resolves, oxygen returns, the lactic acid is flushed out.
The peripheral pain signals generated by the muscle are silenced, breaking the feedback loop to the spinal cord.
The paper highlights several clinical trials validating this exact approach.
Yes. A landmark randomized, double-blind, controlled trial conducted by Abbott and colleagues in 2006.
They took 60 women suffering from chronic pelvic pain and confirmed pelvic floor spasm. They injected 80 units of botulinum toxin directly into the puborectalis and pubococcygeus muscles.
And the objective data from the trial was definitive. The women who received the Botox experienced highly significant reductions in dyspareunia pain associated with intercourse and a massive reduction in non-menstrual pelvic pain.
Furthermore, objective manometry readings, which measure pressure within the pelvis, prove that the resting tension of the pelvic floor muscles drastically decreased. The muscles were finally relaxing.
I found one detail of that study absolutely fascinating regarding the control group.
Oh, yeah. The placebo group received injections into the exact same muscles, but the syringe only contained saline salt water.
Yet the researchers noted that the placebo group also experienced a temporary initial reduction in pain.
Which beautifully validates the mechanism of dry needling we discussed earlier. The mere act of the physical needle penetrating the taut band of the trigger point to deliver the saline caused enough mechanical disruption to provide a temporary reboot to the muscle.
But, as expected, the Botox group had vastly superior, much deeper, and significantly longer-lasting relief because of the chemical blockade.
But there is a deeper layer to how Botox works that I want to explore. Botox stops the motor nerve from firing acetylcholine, forcing the muscle to relax.
Right.
But chronic pain is fundamentally a sensory problem. If Botox is just a motor paralytic, why does it reduce the pain so effectively beyond just stopping the physical cramp?
The paper suggests Botox actually possesses direct analgesic properties. This represents the cutting edge of neuropharmacological research into botulinum toxin.
Now, the primary mechanism is indeed motor blockade, relieving the ischemic pain of the spasm. But recent evidence demonstrates a powerful secondary mechanism. Botox directly acts on sensory nerve terminals.
Wait, if it acts on sensory nerves, it must be targeting their release mechanisms too.
We talked earlier about how the sensitized nociceptors release inflammatory neuropeptides backwards into the tissue substance P and CGRP to cause neurogenic inflammation.
Exactly. It turns out that sensory neurons also rely on snare proteins to facilitate the exocytosis or release of those specific inflammatory neuropeptides.
So when the Botox is injected into the inflamed tissue, it gets taken up by the sensory nerves as well, and it cleaves the snare proteins in the sensory terminals, chemically blinding the nerve's ability to dump substance P and CGRP into the pelvic fluid.
It acts as a dual-pronged assault on the pathology. It prevents the motor nerve from causing the mechanical compression of the muscle spasm, and it chemically neuters the sensory nerve's ability to broadcast inflammatory transmitters, aggressively suppressing the neurogenic inflammation.
By shutting down both the physical cramp and the chemical fire, the massive afferent bombardment of pain signals hitting the spinal cord plummets.
And when the dorsal horn of the spinal cord finally stops receiving that relentless high-frequency input, the central sensitization can finally begin to reverse.
The central nervous system gets the quiet it needs to slowly reset its resting potentials and downregulate its receptors back to a normal baseline.
It is a breathtakingly elegant intervention. You are essentially using a localized chemical weapon to force an entire systemic neurological reset for patients who have suffered in agony for years.
It highlights a vital shift in medical thinking. When we step back and review the journey mapped out in this paper, it completely dismantles the simplistic, compartmentalized view of the human body.
We started with the basic concept of touching a hot stove, a simple input-output mechanism.
But we traced how a single localized pathology, ectopic endometrial tissue, can completely hijack that system.
We saw how the tissue essentially builds its own blood and nerve supply, inadvertently laying high-speed fiber optic cables right into a toxic soup of inflammatory cytokines.
We examined the biophysics of peripheral sensitization, watching as the nociceptors dropped their activation thresholds and began firing nonstop.
Physically remodeling the interneurons of the spinal cord to create central sensitization.
And we explored the evolutionary quirk of viscerosomatic convergence, where a lack of dedicated visceral nerve pathways causes the spinal cord to panic and reflexively lock down the pelvic floor.
We looked at the biochemistry of those locked muscles, watching them suffocate from ischemia and generate their own agonizing feedback loop.
And ultimately, we saw how standard anatomical surgeries completely fail to address these deeply entrenched neuromusculoskeletal loops, requiring an entirely new diagnostic framework and treatments like targeted needling and precise neurotoxin injections to sever the chemical bridges.
For anyone studying biology, or anyone who has ever felt frustrated by a medical system that only looks at one piece of the puzzle, this research is the ultimate proof that the body's systems do not exist in isolation.
You cannot study the reproductive system, the immune system, the nervous system, and the musculoskeletal system as distinct separate chapters.
They are deeply, inextricably interconnected. A biological anomaly in one system creates a massive cascade effect that radically alters the neuroanatomy of the spinal cord and the biochemistry of skeletal muscle.
Understanding those invisible links, moving past the obvious structural damage to trace the complex software errors within the nervous system, that is the absolute frontier of pain management in medicine.
It requires modern practitioners to operate as anatomists, electricians, and biochemists all simultaneously.
The complexity is staggering, and it leaves me with one final lingering thought to mull over, specifically building on the mechanism of Botox.
Oh, what's that?
We just spent an hour discussing how modern science has taken botulinum toxin, a substance evolved by bacteria that is literally one of the most potent deadliest paralytic agents on planet Earth and learned how to safely, microscopically deploy it to cure intractable human pain by meticulously rewiring the chemical synapse.
Yeah, it's
It
incredible.
forces you to wonder, as researchers explore deeper into uncharted rainforests or analyze the venom of deep-sea predators, what other intensely dangerous, lethal substances in nature are out there right now, just waiting to be understood, decoded, and repurposed as the life-changing medical miracles of tomorrow?